Section 3.3 covers truth tables, specifically for negation, conjunction, and disjunction. First off, a truth table is a breakdown of a logic function by listing all possible values the function can attain. They're useful formal tools for determining validity of arguments because they specify the truth value of every premise in every possible case. This might not make much sense to you right now, but as we do some examples in this section and a couple other sections, I think it will become more clear to you. So it mentions this idea of specifying a truth value for every premise in every possible case. Well, classifying a statement as true or false is called assigning a truth value to the statement. Now, the negation of a true statement is a false statement. We've talked about that before. And the negation of a false statement is a true statement. And this can be shown in a truth table. And this is exactly what it's going to look like. It is a table. It will have, in this case, since we're just talking about one statement P, it will have these two values here. P can either be true or it can be false. That's the only possibility right there. P can be true or it can be false. Now, the negation of P, if P starts out to be true and we negate a true statement, it becomes a false statement. If we start out with a false statement and we negate it, it becomes a truth statement. Now, this is in chart form exactly what this said right here. The negation of a true becomes false. The negation of a false becomes true. So this is a very simple chart for the truth table for negation. Let's say you've got a friend that says to you, I visited London and I visited Paris. In order to determine the truth value for this statement, we can break it down into two simple statements. I visited London, I visited Paris. Now this is called a conjunction because we use the word and. We've had that definition before. The only time this statement is true is if both P and Q are true. This truth table should help you understand why a conjunction is true only when both simple statements are true. It's like this. Here's the two simple statements. I visited London, that's the P. I visited Paris, that's the Q. Your buddy could be telling you the truth about visiting London, and he could be telling you the truth about visiting Paris. That's what this first row is trying to show you, that the P part of the statement is true, the Q part of the statement is true, and if both simple statements are true, that means that the conjunction is true. Another possibility is that your buddy's telling the truth about going to London, but he lied about the Paris part of the trip. So that's true, false. If he puts those two things together, that is a false conjunction, because for an and statement to be true, both parts must be true. Another possibility is he lied about going to London. He did tell you the truth about going to Paris. That's this right here. The London statement is a falsehood, but the Paris statement is true. If you put that together in one and statement, you are telling a lie because both parts are not true. And the last thing is he could be lying about going to London and he could be lying about going to Paris. That's false, false, and that's going to give you a false there also. So the only time the conjunction, which is what this is with the and, the only time that is true is when both simple statements are true. Now, another thing that's important here is that when you have a truth table for two simple statements like this, these were two simple statements, your beginning two columns will always look like this. A P column, a Q column, and notice what this does. The P goes T, T, F, F, and the Q goes T, F, T, F. We will always use that configuration. We could put it in a different order if we wanted to, but that's the order you will always see in books and your homework, things like that. So that's the way we're going to organize the truth table. Now, what if your friend actually said, I visited London or I visited Paris? When would this compound statement be true? I visited London or I visited Paris. And then the question is, when would this compound statement be false? So let's do the same thing and look here before we answer that question. Here's our simple statements. I visited London, I visited Paris. So let's do the same thing. He might be telling the truth about going to London. He might be telling the truth about going to Paris. That's this right here. And when you put true or true together, you get a true. Next is the idea that he's telling you the truth about going to London, and he lied about going to Paris. That's TF. When you do true or false, it is a true statement. Think about being a kid, and your mom says, where are you going after school? And you say, I'm either going to basketball practice or I'm going to the chess club. If you go to one of those or the other, are you telling the truth? Sure. If you went to basketball but didn't go to chess, you've still told the truth because you said or. That's what this is. True, false. This idea here is you lied about London. You told the truth about Paris. So you've said, I'm going to London or I'm going to Paris. You did go to Paris, so you have told the truth. So notice those first three in that column are all true. But here's where you get in trouble. I visited London. I visited Paris. Both of which is a lie. So if you put it together as or, have you told the truth? No. So a disjunction is false only when both component statements are false. Go back to mine as when you were a kid. Mom, I'm going to basketball practice or I'm going to the chess club. What if you went to the swimming pool instead? You lied. You didn't go to basketball practice. You didn't go to the chess club. You were not where you said you would be. You have lied, and therefore we get an F right there. So the only time an and statement is true is if both P and Q are true. The only time an or statement is false is if both P and Q are false. So those two statements might help you keep straight the difference between the two truth tables. So a little conclusion here. Negation, which is the tilde, is not. The negation of a statement has the opposite truth value from the original statement. The conjunction, that's the upside down V, kind of looks like an A, which would stand for and. The only case in which a conjunction is true is when both component statements are true. Disjunction, which is the V, is or. The only case in which a disjunction is false is when both component statements are false. So let's construct a truth table for Q or not Q. So there's only one simple statement, Q. Do you know how many rows you would need? Well, if I only have one simple statement, Q, what can Q be? Q can either be a true statement or it can be a false statement. The only thing I then need to do is fill in what it will be for not Q. If the original statement was true and I negate that, we know it becomes false. If the original statement was false and I negate that, it becomes true. Now, I'm not finished with this whole thing. This wants me to also do Q or not Q. So I need to extend my chart and look at Q or not Q. So now I'm looking at these two entries under the disjunction truth table columns. True or false will produce a true. False or true produces a true. Remember, the only time an or statement is false is if both of these are false. How about we want to do a truth table for not P and Q? So now we've got two simple statements, P and Q. Do you know how many rows we need? Well, think about P. P is going to go T, T, F, F. How's Q going to go? Q will go T, F, T, F. So anytime you have two simple statements, you will need 4 rows. And those initial 4 rows will always look like this. So here it is again, just written out neatly. Now that's just the P and the Q and the T, T, F, F, T, F, T, F, but we have to build this statement in our truth table. So we have the P, we have the Q, we will need P and Q, but then we will also need the negation of P and Q. So this is your way to design your truth table. You have to take it one little bit at a time until you have built all the way up to the final statement. And you have to remember your order of operations. I have P and Q right here because it's inside parentheses, and I know I need to do what's inside parentheses first. Then the negation of P and Q. So you can look back at the chart from a couple screens ago if you want, or think about this. The only time an and statement is true is if what? If both of these statements are true. So that's the true. The rest of these are false. And if I want to negate that column, negate a true, it becomes false. Negate a false becomes true. That one becomes true. And that one becomes true. Let's make a truth table for not P or not Q, starting with our basic P and Q columns. This one tells me I need to have a separate column for not P, so I'll do that one. I need to have a separate column for not Q. I'll do that one. And then I can do not P or not Q. So if I negate P, that's going to take all of these and flip-flop them. So it becomes false, false, true, true. Not Q tells me to take all of these and flip-flop them. False, true, false, true. And now put these two columns together using the connector OR. Remember, OR is only false if both individual statements are false. These two are false, so I will have a conclusion of it being false. The rest of these will be true. As long as you have at least one T, as long as you have at least one T, then you know your conclusion will be true. Now that we've done a few truth tables, you might understand that definition I listed on the first screen, and that is this. A truth table is a breakdown of a logic function. This is an example of a logic function by listing all possible values the function can attain. These are the possible values that that function can attain. They are useful formal tools for determining the validity of arguments. This can be considered an argument because they specify the truth value of every premise in every possible case. These are your premises in every possible case.